Hello, I welcome you all to this another interesting screencast. The problem reads: a boat has an initial speed of 16 feet per second. If it increases its speed along a circular path of radius rho equal to 80 feet at the rate of v dot, which is acceleration equal to 1.5 s in units of feet per second, where s is in feet, determine the time needed for the boat to travel s equal to 50 feet. This problem is coming from the engineering mechanics dynamics 14th edition by RSC Hibbeler. Alright, so before I do anything, let me talk about just the basic equations that we're going to be using. So we have velocity, which is the time derivative of position. We have acceleration, which is the time derivative of velocity. From the two equations, we do have the derived one, which is a ds equal to b dv. From these three basic kinematic equations, we are able to derive quite a couple depending on the boundary conditions. But we do have the common equations when acceleration is constant at t equal to 0, s naught and v naught. And from this, we're able to derive the following: s is equal to s naught plus v naught t plus half ac t squared. And then we have v is equal to v naught plus act, and v squared is equal to v naught squared plus 2ac s minus s naught. So we have a boat here that is traveling in a circular path. So let me just try and draw this path. So let's say this is the path, and we've been told that the radius for this particular path, let's say the radius is rho equal to, so this is the radius of our circular path. Rho is equal to 80 feet. That's a radius. Okay, so imagine this is our starting point for our s, and we are trying to find trying to work out the time needed for the boat to travel 50 feet. Okay, all right. So what do we do here? Of course, our acceleration is a function of position. So straight away we are going to go for this equation, and once we use this equation, we determine velocity. Velocity, which will be a function of position, and once we have that, we need to find the time. Then we come and use this particular equation. Okay, so we're using two equations, that one and that one, right? And after everything, then let's see what happens. So we have ADS equal to V dV. Okay, so from this equation, we are going to apply the integrals like so. So we are moving from 0 to s. Here we are starting from we do have some initial, so say v naught, then v. Okay, we do have some initial speed. Our a here is equal to v naught, which is equal to 1.5 s. All right, and our v naught here is I equal to 16. What else? And that's about it. So let's work out. So we'll have 0 to s of 1.5 s ds equal to integral from 16 to b, then v dv. Then working out this, we'll have 1.5 s squared divided by 2, right? Equal to v squared minus 16 squared divided by 2. All right. Therefore, our v is just going to be equal to square root of 1.5 s squared plus 16 squared, right? All right, so found our v, which is a function of s. So use this equation now. So say v equal to ds dt. So we can write this equation as dt is equal to, since v is a function of s, so we'll bring it underneath like so. Our v, we already have it, is let me put the integrals. So we're going to integrate this, just means finding the area. So here we are starting from 0, the time, to t, and then here ds, we are starting from 0 also to s. But we already know what s is, but we can okay, we indicate it here. Our s is equal to 50 feet. Okay, that's 15. Everything is in feet. Our v, we already know it is square root of 1.5 s squared plus 16 squared. Plugging this, then we are going to have t is equal to integral from 0 to 50 of 1 divided by root of 1.5 s squared plus 16 squared. Okay, here we go, 16 squared. Okay, yes. So of course this will allow us to find the time. It's a definite integral. Of course you can solve it analytically, but for me, I'm going to use a numerical technique to solve this. It may take a little bit of time for me to solve, but if you have tables already given, you know those standard tables where equations for integrals are already given, you can just plug this, replace this, and solve it. But in an event that you do not have that information and so on, I guess trying to solve this integral will take a little bit of time. So I'll use a method myself called Simpson's rule. Okay, Simpson's rule. This is a numerical technique that you can use to solve integrals, and let me just express it how it is. So given a function from a to b, of let's say of f of s, like in our case our f of s is our v, so ds. So this is approximately equal to ds divided by 3 ds divided by 3, and then we have f s naught f of s naught plus 4 s1 plus 2. So we alternate between 4 and 2 plus, let's say we have another 4, then 3, then plus s n minus 1. Okay, then plus the last one will not have any coefficient, like so. Okay, where del s is equal to b minus a divided by n, and n is equal to number of subdivision, number of even subdivisions. Okay, so subdivisions. So basically what we are doing is we are dividing the area, okay, under the curve into a number of subdivisions, which we later on sum up together using this technique. Like I said, this is a numerical technique. You don't have to do this if you can solve this quickly. Okay, the idea is time, but if tables are given, then go for them. So having said that, let's solve this using this technique. So in my case, I'm going, in my case, my n, I'll choose n equal to 4. This is number of subdivisions. Again, I said they have to be even, so you can go is even numbers. The more the subdivisions, the more the solution converges, slowly converges, or converges to the actual analytical solution, right? So the more the number of divisions, okay, the higher the accuracy of the solution. All right, and then we have our a equal to 0 and our b equal to 50. Okay, and our function itself is this is 1 divided by root of 1.5 s squared plus 16 squared. Okay, so we do have all the information. All we need to do is plug in. So let's find our del s. Like we said, this is equal to 50 minus 0 divided by 4, and this just gives us, it's a 12.5, right? That's 50 divided by 4, that's a 12.5. So if we are to draw this on the number line, basically what we are saying is we are to draw this. This is what we are saying, right? 1 2 3 4, like so. Okay, so let's draw this on the number line. So we have this value there, this value, this value, this value, this value, and this value. So if we are to record this, so we are saying from 0 to 12.5, then to 25, then to 25 plus 12.5, that's 37.5. Okay, and then finally to 50. Okay, so how many points do we have? So here, this distance here is the one we are calling del x. Okay, all right. So let's write down. So we do have this equation already. We are using this equation here. So I just want us to go directly to find these values. So say f of so this is our 0, this is our 1 2 3 4. Okay, So for us, we are just going to go up to 4. So we are saying, if we are to write this, we are going to say integral from 0 to 50 over f of s, which you already know. Okay, and this is approximately equal to 4.5 divided by 3, and then we have f of 0, okay, plus 4 f of 4.5 plus 2 f of 25 plus 4 again, 1 2 3 4 again, f of 37.5, and then finally just f of 50 without any coefficient. So let's find these values. What is our f of 0? We need to plug in our 0 in our function, which is this one, okay, where we have s. So let me write down this equation in advance. Square root of 1.5, we have a 0 there, squared, and plus 16 squared, and we close this, right? This is fine. So this one gives us a 0.0625. Then we have f of 12.5 with a 4 there. I'll need to multiply it in advance, then I'll sum them up, or even without that I'll come and work them out. So there we go. That one is 4.5. Right. What do we get? We have a 0.04516. Okay, one significant figures, minimum of 4 for me, 4516, 4516. Okay, then I have f of 25 equal to 25. This is a 0.02895, and then f of 37.5. What do we have? Is it 2895, 37.5, 37.5. So we have a 0.02056, and finally f of 50. Okay, 50. This gives us a 0.01580. Okay, therefore, alright, so our time therefore is equal to integral from 0 to 50 of our function, and our solution is approximately equal to 1.66 seconds. Okay, I guess we are done. You can check this out using the analytical solution so that you compare with our approximate solution and see how close we were. Alright, so I hope this video was helpful. Let me just outline this time for us. I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.